Here are 100 facts about black holes to fall asleep to. Spaghettification is real. If you fell into a stellar mass black hole feet first, the gravity at your feet would be drastically stronger than at your head. This tidal force would stretch you out like spaghetti, a process scientists literally call spaghettification. It's not instant, you'd feel the stretching as bones and tissues elongate painfully before you're atomized. You'd never see someone fall in. If someone fell into a black hole, you wouldn't see them past the event horizon. Instead, they'd appear to freeze in time, their image growing dimmer and redder. Eventually, they'd fade completely. To outside observers, they never fully disappear, but they're gone. Black holes can move. They're not stationary cosmic vacuum cleaners, they can move through space at millions of miles per hour. Some have been kicked out of their galaxies entirely after collisions, becoming rogue black holes, wandering through intergalactic space silently and invisibly. Black holes can sing. In 2003, astronomers found a black hole in the Perseus galaxy cluster that emits a note, a B-flat, 57 octaves below middle C. It's sound in space, carried through hot gas. You'd never hear it, but it's the deepest known note in the universe. They can evaporate. Very, very slowly. Hawking radiation allows black holes to lose mass, slowly evaporating over unimaginable spans of time. A black hole with the mass of the Sun would take around 10,671,067 years to vanish, far longer than the age of the universe. Black holes can grow to unfathomable sizes. The largest black holes, called supermassive black holes, can weigh billions of times more than our Sun. TON 618 is one of the largest ever discovered, with a mass of 66 billion suns. If it were placed at the center of our solar system, it would engulf every planet out to Pluto. There's a black hole in the Milky Way. Right now, at the center of our galaxy, sits Sagittarius A*, a supermassive black hole with 4 million times the mass of our Sun. It's relatively quiet, but it occasionally flares with energy, suggesting it's still feeding occasionally. A black hole could eat a star, and you could see it happen. When a star ventures too close, the black hole rips it apart in a tidal disruption event. This tears the star into glowing plasma, forming a bright flare that lasts months. We've observed several of these grisly cosmic meals. They might be gateways, but probably not. Some theories suggest black holes might connect to other universes via wormholes, or that what's inside a black hole might not be a singularity at all. These are speculative but deeply captivating ideas, and a few physicists believe it's possible we could one day test them. Time slows near a black hole. The closer you are to a black hole, the more slowly time passes for you compared to an outside observer. Near the event horizon, minutes for you could be years for someone further away. A real-life version of time travel. Black holes are perfect spheres, kind of. According to general relativity, an isolated, spinning black hole is perfectly smooth and featureless, no bumps or irregularities. All its complexity is hidden behind the event horizon. They have no hair. This is a real term in physics. The no-hair theorem suggests that black holes can be completely described by just three things: mass, spin, and charge. All other information, like the nature of the matter that formed them, is lost. They're not actually holes. Despite the name, black holes aren't holes in space, they're objects with mass, volume, and gravitational pull. Calling them holes comes from the fact that nothing can escape once it crosses the event horizon. You could orbit one safely. If you stayed far enough away, you could theoretically orbit a black hole just like a planet orbits a star. In fact, many stars do orbit black holes without being pulled in. There are likely millions in our galaxy. Our Milky Way probably harbors over 100 million black holes. Most are invisible, quietly floating through space. Many formed from massive stars that died long ago. Some might be primordial. Some theories suggest tiny black holes might have formed just after the Big Bang. If they exist, they'd be smaller than atoms but incredibly dense. We've never found one, yet. Tranquil and mind-bending facts for drifting off. Black holes create beautiful light shows. As matter falls in, it heats up and emits brilliant X-rays and visible light. The accretion disk glows with such intensity that it's sometimes the brightest object in a galaxy. They're like cosmic sculptors. The gravity of black holes shapes galaxies, influences star formation, and may be critical to how galaxies form in the first place. They're not just destructive, they're creative forces too. You'd never notice falling into a supermassive one, at first. Unlike a stellar black hole, the tidal forces near the event horizon of a supermassive black hole are weak. You could fall through without feeling anything initially. The horror comes later, deeper in. They merge with others. When two black holes orbit each other, they emit gravitational waves and spiral inward. These cosmic dances end in a merger that sends ripples through spacetime, gravitational waves that we've detected from Earth. They're testbeds for theories of everything. Studying black holes might help unify general relativity, gravity, and quantum mechanics, the two biggest, yet incompatible, theories in physics. Photons can orbit them. There's a region near a black hole where light itself can orbit in circles. This is called the photon sphere, and it creates the glowing ring seen in the famous Event Horizon Telescope image of M87's black hole. You might see the back of your head. Near a black hole, light can be bent so much it curves completely around it. If you looked away from the black hole, some light from behind you might curve around and reach your eyes, letting you see the back of your head. They're part of the universe's grand cycle. Stars are born, live, and die, sometimes ending as black holes. Over time, black holes might dominate the far future universe, before they too fade away into nothingness through Hawking radiation. Their silence is comforting. Black holes don't make noise. They don't glow. They sit in the dark, quietly distorting time and space. There's a strange calm in their eternal stillness. Black holes can create echoes in spacetime. After two black holes merge, the newly formed one rings like a struck bell, emitting gravitational waves. These faint echoes, if detected, could reveal whether the event horizon is smooth or hold surprises beyond our current physics. Their gravity warps the path of light. A black hole bends light so severely that it can cause distant objects behind it to appear distorted or multiplied. This is called gravitational lensing. Einstein predicted it, and we've seen it in space telescopes. There's a theoretical firewall inside. One controversial theory proposes that inside a black hole, instead of gently falling toward the singularity, you'd hit a violent wall of energy, an information firewall, that breaks the laws of physics as we know them. They could contain an entire universe. Some cosmologists speculate that what appears to us as a black hole might actually contain a whole universe inside it. From the inside, that universe could expand like our own Big Bang. They could reveal the fate of information. One of the deepest puzzles in physics is whether information about matter that falls in is truly lost. The black hole information paradox challenges fundamental laws of quantum mechanics and is still unresolved. You can't escape even at light speed. Once something crosses the event horizon, even if it could travel at the speed of light, it couldn't get out. That's because spacetime itself is being dragged inward faster than light can move. Their core is a singularity. General relativity says the heart of a black hole is a singularity, where matter is crushed to infinite density, and spacetime curves infinitely. It's where our current physics completely breaks down. They affect quantum particles near them. Quantum effects near the event horizon can create virtual particle pairs, which leads to Hawking radiation. This tiny process eventually causes the black hole to lose mass, bit by bit. They don't actually suck things in. A common myth is that black holes vacuum up everything nearby. But their gravitational pull is only dangerous up close. At a distance, they behave just like any other object of the same mass. Miniature black holes could exist. Some theories predict microscopic black holes might exist or could be created in particle accelerators. None have been found, but if they exist, they could reveal new physics. The closest known black hole is surprisingly nearby. In 2024, scientists confirmed a black hole just 1,500 light-years away, in Gaia BH1. That's in our galactic backyard, and it's silent, invisible, and completely undetectable without precise measurements of nearby stars. They can power galaxies. Some black holes at galactic centers are active, feeding constantly. The material swirling into them emits so much energy that it can outshine the rest of the galaxy. These are called quasars. They may help galaxies thrive. Black holes don't just destroy, they regulate star formation by releasing jets of energy and matter that prevent galaxies from forming too many stars at once, keeping things balanced. They can stretch time infinitely. For someone falling into a black hole, the outside universe would seem to speed up infinitely. In theory, you could watch the entire future of the universe unfold in a blink, just before being destroyed. Some black holes have magnetic fields. While black holes themselves can't hold magnetic fields, the plasma spiraling around them can generate massive ones, thousands of times stronger than anything on Earth. They help test Einstein's theory. Every time we study the orbit of stars near Sagittarius A** or detect gravitational waves, we're stress testing Einstein's general relativity, and so far, it's passed every test. You could orbit inside a safe zone. A region called the innermost stable circular orbit marks the last possible safe orbit before plunging in. For spinning black holes, this orbit gets closer than for non-spinning ones, letting you flirt with danger. They can throw stars away. Sometimes, instead of swallowing stars, black holes slingshot them away at incredible speeds, tossing them out of galaxies entirely, becoming rogue stars drifting through the cosmos. Their mergers make ripples in reality. When two black holes collide, they generate gravitational waves, literal ripples in the fabric of spacetime, which we can now detect with observatories like LIGO and Virgo. They influence star birth thousands of light-years away. The jets and radiation from black holes can compress interstellar gas clouds far beyond their local area, triggering new waves of star formation far from their own galactic core. They're among the most efficient energy sources. As matter falls into a black hole, it can convert up to 42% of its mass into energy, far more efficient than nuclear fusion, which only converts about 0.7%. They form from stellar corpses. Most black holes are born when massive stars run out of fuel and collapse under their own gravity. In a flash, their light is gone, leaving a dense remnant in eternal silence. They may be the universe's final survivors. In the far, far future, after all stars have burned out and galaxies have dissolved, black holes might be the last structures left. They'll slowly evaporate over trillions of years. They're part of the night sky's hidden symphony. Although you can't see them with your eyes, the motions of stars and gas near black holes shape how galaxies rotate, evolve, and cluster. They're the invisible conductors of cosmic music. Their beauty is found in their shadows. The iconic image of a black hole from the Event Horizon Telescope is actually the shadow of its event horizon, outlined by glowing gas. It's the silhouette of the unknowable, pure negative space. 76. Black holes have no surface, only a horizon. Unlike a star or planet, a black hole doesn't have a physical surface you could touch or land on. Instead, it has an event horizon, a boundary in spacetime beyond which nothing can escape. Crossing it is like slipping off the map of the universe. No matter, energy, or even information can get back out, and what's inside remains forever hidden. 77. A black hole's mass warps spacetime into a funnel. Einstein showed that mass curves spacetime, and a black hole, with extreme density, stretches that curvature into a steep, funnel-shaped well. Visualized in 2D, it's like a trampoline with a bowling ball pressed into it, but in reality, this funnel drops through the fabric of four-dimensional spacetime, forming a hole with no bottom. 78. time near a black hole moves infinitely slower. This effect, called gravitational time dilation, means that to a distant observer, time appears to slow to a halt at the event horizon. If you hovered just outside it, you could watch eons pass in the universe beyond while only minutes tick by for you, until eventually, even that concept of time would blur. 79. Spaghettification is real, and horrifying. As you fall into a stellar mass black hole feet first, gravity pulls more strongly on your legs than on your head. This tidal force stretches you into a thin, elongated shape, literally spaghettifying your body. At a certain point, even atoms are torn apart. And the process is not gentle, it's violent, fast, and final. 80. At their cores lies a mathematical abyss. The singularity at a black hole's center is where the equations of general relativity hit infinity. It's not just a physical point, it's a region where density becomes infinite, volume collapses to zero, and time may cease to have meaning. Physicists believe that understanding this singularity may require a theory of quantum gravity, which we don't yet possess. 81. They might be gateways to other universes. Some speculative models, especially those combining general relativity and quantum theory, propose that a black hole could tunnel into another universe. What we see as the event horizon might be an entrance, and the singularity could be the Big Bang of another cosmos. It's untestable, but profoundly poetic. 82. A white hole is a theoretical opposite. Where a black hole traps everything inside, a white hole is the reverse. It ejects matter but never allows anything in. They're mathematically possible under relativity but have never been observed. Some scientists propose they might be connected, forming a kind of cosmic plumbing system. 83. We've imaged one using a global telescope network. In 2019, scientists used the Event Horizon Telescope, a network of radio telescopes across Earth, to image the shadow of the black hole in galaxy M87. What we saw wasn't the black hole itself, but its silhouette. A dark center surrounded by a glowing, lopsided ring of heated plasma swirling at nearly light speed. 84. Black hole collisions shake the universe. When two black holes merge, they warp spacetime so powerfully that the resulting gravitational waves ripple outward at the speed of light. These waves stretch and squeeze space itself. We've detected these subtle tremors with laser interferometers like LIGO, capturing cosmic events billions of light-years away. 85. The largest black holes are unfathomably massive. Called ultramassive black holes, these beasts can weigh over 50 billion times the mass of the Sun. They sit at the hearts of enormous galaxies like TON 618, whose black hole may be as wide as the entire solar system and whose gravitational pull dominates everything for light-years around. 86. They can flicker in X-rays when feeding. As matter falls into a black hole, it forms a hot, turbulent disk. This disk emits X-rays, and the brightness can vary from second to second. This flickering isn't random, it reflects waves of magnetic turbulence, chaotic motion, and infalling matter crossing critical boundaries near the event horizon. 87. Quantum mechanics suggests they radiate heat. Stephen Hawking famously showed that black holes aren't perfectly black, they can emit Hawking radiation due to quantum effects near the horizon. Over unimaginable timescales, this radiation can cause them to lose mass and eventually evaporate, leaving behind, what? We still don't know. 88. Black holes may encode their contents on the horizon. According to the holographic principle, all the information about the matter that falls into a black hole might not be lost, but rather encoded on the 2D surface of the event horizon. This idea could bridge the gap between relativity and quantum theory, and hints that the universe itself may be holographic. 89. Supermassive black holes can go dormant. These giants aren't always active. Some are currently quiet, consuming little to no matter and emitting no jets. They may have gone silent for millions of years, waiting for a new stream of gas or an unlucky star to awaken their terrifying hunger again. 90. The Milky Way's central black hole is surprisingly calm. Sagittarius A*, the black hole at the center of our galaxy, is about 4 million times the mass of the Sun, but it's relatively inactive, currently only nibbling on small amounts of gas and dust. It flares occasionally, sending out a whisper of X-rays, but nothing like the raging quasars of distant galaxies.
91. Black holes can form in dense star clusters. Most black holes come from the collapse of a single, massive star. But in tightly packed star clusters, a different path unfolds. Stars can collide and merge repeatedly in a chaotic cosmic dance, forming a supermassive star that then collapses into an intermediate mass black hole. These elusive black holes are heavier than stellar black holes, but far smaller than the supermassive giants in galactic centers. Astronomers believe clusters like these could be the nurseries, where the seeds of the universe's largest black holes were born, long before galaxies had fully formed. 92. Echoes of early black holes may be hidden in ancient light. The cosmic microwave background, CMB, is the oldest light in the universe, a 13.8 billion-year-old afterglow of the Big Bang. Some physicists believe that black holes forming shortly after the Big Bang could have subtly warped this ancient light. These distortions, though incredibly faint, might act as fingerprints of primordial black holes. If we can detect them, we could uncover secrets about how structure formed in the early universe, perhaps even discovering that black holes came before galaxies. 93. Light can orbit a black hole in perfect circles. Briefly, at a precise distance from a non-rotating black hole, lies a fragile boundary called the photon sphere. Here, photons, particles of light, can orbit the black hole in a perfect circle, endlessly looping in a gravitational ballet. But these orbits are inherently unstable. A tiny disturbance will either send the photon spiraling into the black hole or escaping into space. If you could hover nearby, you might see your own image, warped and delayed, circling the black hole multiple times before reaching your eyes. 94. A wormhole might be hiding behind the horizon. Einstein's equations allow a bizarre possibility. If a black hole connects to a white hole, the two could form a wormhole, a tunnel through space-time. Known as an Einstein-Rosen bridge, this hypothetical path could connect distant parts of the universe, or even different universes entirely. Unfortunately, these wormholes would likely collapse instantly if anything entered them. Still, the idea lingers in theory and fiction alike, beckoning us with the dream that black holes might be more than graves. They might be passageways. 95. The universe may contain trillions of black holes. Black holes are far more common than we once imagined. In our own galaxy, astronomers estimate there could be as many as 100 million stellar mass black holes, quiet, invisible, scattered like hidden mines across space. Extrapolated to the whole observable universe, that means trillions of black holes, perhaps even more. Most of them are invisible, lurking in darkness, isolated, haunting the galactic outskirts. They outnumber stars in some regions, and yet we barely notice them until they feed. 96. Black holes could be made of exotic matter or fields. Some black holes may not be what we think. Theories in high-energy physics suggest black holes might form not just from collapsing stars, but from exotic matter, such as hypothetical boson fields or dark matter particles. These would form black hole mimickers, possibly stable objects with unusual internal structures, or no singularity at all. Detecting one would change our understanding of matter itself, opening a window into physics beyond the standard model, and perhaps explaining the mystery of dark matter. 97. Crossing a supermassive black hole's horizon might feel like nothing. If you fell into a stellar mass black hole, you'd be shredded by tidal forces well before the event horizon. But if you fell into a supermassive black hole, millions or billions of times the mass of the Sun, you wouldn't feel much at the horizon itself. It's so vast, and the gradient of gravity so gentle that you'd float across in silence, unaware you'd passed the point of no return. It's strangely peaceful. Only later, deep inside, would the crushing forces take hold. 98. Black holes can steal stars and launch them at galactic speeds. In dense galactic cores, black holes can tear stars from each other's orbits. If a binary star system strays too close, one star may be devoured, while the other is flung outward at incredible velocity, becoming a hypervelocity star. Some of these exiles have been observed racing away from the Milky Way at over 1,000,000 miles per hour, like glittering cannonballs shot across the void, marking where black holes have disrupted peaceful orbits. 99. Some physicists wonder if consciousness could be stored in a black hole. This is speculative and deeply philosophical. But some researchers wonder, if all information about matter that falls into a black hole is preserved, as the holographic principle suggests, could the pattern of a conscious mind survive, encoded on the event horizon? Is identity simply a quantum arrangement? And if so, can it ever truly be lost? This question remains unsolved, but it's on